So thank you so much. So let me just give an outline of my three talks. So in lecture 1, I will explain what is the amplituhedron and also what is a cluster algebra. I think the latter is going to be helpful for the 2 talks that follow mine. In my second talk, I will discuss in detail the m equals 2 amplituhedron and connections to cluster algebras. And in my third talk, I will discuss the m equals 4 amplituhedron and connections to cluster algebras. So this first talk is meant to be quite introductory. So please feel free to interrupt if you have any questions. I arrived this morning after a red-eye flight, so if I'm not making any sense, you're also welcome to correct me. Okay, so in order to talk about the amplituhedron, I need to first talk about the Grassmannian and the positive Grassmannian. So the Grassmannian, GRKN of R, is the set of all subspaces in an n-dimensional vector space which have dimension k. And we will represent elements of the Grassmannian by full rank k by n matrices C. And then the row span of such a matrix represents a subspace. So we want to talk about Plücker coordinates of the Grassmannian. So if I have capital I, a k-element subset of the numbers 1 through n, then the Plücker coordinate P sub I of C is the minor of C in columns I. So for example, say my k is 2 and my n is 4, and my matrix C is 1, 0, 0, minus 3, 0, 1, 2, 1, then the row span of C gives me a 2-dimensional subspace of R4. And the Plücker coordinate, say, P1, 3 of C, is the determinant of the submatrix located in columns 1 and 3, which is 2. Okay, so that's the Grassmannian and the Plücker coordinates. And now the totally non-negative, or TNN, and sometimes called positive Grassmannian, GRKN greater than or equal to 0, is the subset of GRKN where my Plücker coordinates, P sub I, are non-negative for all I ranging over the k-element subsets of 1 through n. And so this object first arose in work of Lustig, where he defined the totally positive part of a real reductive group and the positive and non-negative parts of generalized partial flag varieties, of which the Grassmannian is a special case. And then there was follow-up work by Connie Reach, in which she gave a cell decomposition for the non-negative part of G mod P. And then there was this very influential preprint of Postnikov in 2006, where he discussed the special case of the Grassmannian and worked out a beautiful indexing sets for the cells. So, okay, so let me talk about the cell decomposition of the TNN Grassmannian. So we can partition the TNN Grassmannian into pieces based on which Pluker coordinates are strictly positive versus equal to 0. So if we let M be a collection of k element subsets of 1 through n, then we can define a corresponding subset of the TNN Grassmannian consisting of all elements in the TNN Grassmannian where our Pluker coordinate p sub I is strictly positive if and only if I belongs to our collection. Okay, so I'm just going to say, okay, you give me your favorite collection of Pluker coordinates, and then we will define the subset of the TNN Grassmannian where my Pluker coordinates are strictly positive if and only if they belong to the collection, and otherwise the Pluker coordinates must be 0. And so by work of Postnikov, and in a using slightly different definitions, we know that every non-empty stratum, SM, is actually a cell. So homeomorphic to an open ball. And moreover, the cells glue together nicely. And this collection of cells is actually a CW complex. Okay, so what we've done so far is just define the TNN Grassmannian and define a stratification into cells. They're called positroid cells. Yes, I should write that. Yes, and positroid is meant to sound like matroid, so this is related. So one can talk about the matroid stratification of the entire Grassmannian, where you don't impose the non-negativity, and then what you get when you superimpose the matroid stratification onto the TNN Grassmannian is this decomposition into positroid cells. Okay. And I mentioned that in Postnikov's preprint, he classified all of these non-empty cells. So these cells they've been classified, and they are in bijection with various combinatorial objects. One nice indexing set is equivalence classes of Playbit graphs. Which I'll say more about in my third talk. Question? Okay, so now I want to define this object called the amplituhedron. And this object was defined by physicists Arkani Hamed and Trinka in 2013. So, okay, so how do we define the amplituhedron? So first we're going to fix positive integers n, k, and m with k plus m at most n. And we're also going to fix a matrix Z, and this will be an n by k plus m matrix with maximal minors positive. So this is an n by k plus m matrix. Okay, so this matrix is going to be a sort of a tall and skinny matrix because of this inequality. And so the maximal minors will be the k plus m by k plus m minors, and we're requiring that these are positive. And now I'm going to define a map, Z tilde. So this is going to be a map from the T and N Grassmannian, GRKN, to another Grassmannian of k planes in k plus m space. And this is a map that takes the k by n matrix C to the matrix product CZ. So Z is n by k plus m. So this matrix product CZ is a k by k plus m matrix. And again, so remember, I'm always identifying matrices with their row span. So this matrix C represents an element in the T and N Grassmannian of k planes in n space. And I will identify this k by k plus m matrix with its row span. And in order to convince you that this map is well defined, let me just point out that one can show that the fact that Z has maximal minors positive implies that this matrix has full rank and hence represents a point in this Grassmannian. Okay, so what I've done so far is fix n, k, and m and a matrix Z, and then I've defined this map Z tilde from this T and N Grassmannian to a related Grassmannian. And now what's the amplituhedron? It's going to be the image of the T and N Grassmannian under this map. So the amplituhedron, which depends on these three numbers n, k, m, together with the matrix Z, is by definition the image of the T and N Grassmannian under this map. And so this is going to be a subset of the Grassmannian of k planes in k plus m space. Okay, so maybe I should say a few words about motivation here. So the motivation is coming from n equals 4 super Yang-Mills theory. And so there was this famous recurrence, BCFW recurrence. BCFW stands for Brito, Cachazo, Fang, and Witten. And this BCFW recurrence, which is from like 2005, expresses scattering amplitudes as sums of rational functions of momenta. And in this recurrence, so this recurrence has a whole bunch of terms, and the individual terms have spurious poles, meaning singularities not present in the amplitude. So when you sum all of the terms up, you get something where these poles have disappeared. But the BCFW recurrence itself is this sum of terms where you get some spurious poles. And then in 2009, Hodges observed that in some cases, the amplitude is actually the volume of a polytope. With these spurious poles arising from internal facets of a triangulation. Okay, and so motivated by these examples that he looked at, he asked, is the scattering amplitude the volume of some geometric object? And then in this 2013 work of Arkhani Hamed and Trinka, they said yes, and the geometric object is the amplituhedron. And then in this paper, which had all these constructions, but the actual statements were largely conjectural, they interpreted the BCFW recurrence as giving a quote-unquote triangulation of the amplituhedron. Okay. All right. So that's all I was going to say about the physicsy motivation, but if you have any questions, I can try to answer them.
Which dimension has the amplituhedron?
So the amplituhedron is full dimensional inside of this Grassmannian, and so it has dimension k times m. But for the application they had in mind, which is these scattering amplitudes, the relevant for the scattering amplitudes in n equals 4 super Yang-Mills, and for the BCFW recurrence, the relevant case is where little m equals 4, and so then it'll be a 4k dimensional object. Uh-huh.
Do we get genuine non-spurious poles from the boundary of the amplituhedron itself?
Yes, yes. So you get actual poles from the boundary. Yeah. Okay. So now let me talk about a few examples. So I guess one point I want to make is that the amplituhedron generalizes lots of nice objects. So first of all, if Z is a square matrix, then the map Z tilde, which is basically given by matrix multiplication, is an isomorphism. So Z tilde will be injective and then the amplituhedron just recovers the TNN Grassmannian. Okay, so that's sort of a boring example. The next example, which is more interesting, is when, say, k is 1 and m is 2. And then the claim is that this amplituhedron, which will lie inside grk, comma k plus m, which here is gr1, comma 3, which is the same as P2, is a polygon in projective space. So let me just say why. Let me just convince you that this is true. So in this k equals 1 example, so n will be general, but k is 1. Then my map z tilde is going from grk, comma n, which is gr1, comma n. So z tilde will be a map taking points in the non-negative part of gr1, comma n. So all of these coordinates are non-negative, and it maps this element of the TNN Grassmannian to the matrix product of this row vector times my matrix Z, which is an n by k plus m matrix, or in other words, an n by 3 matrix. And now notice that if I use EI to just denote the 0, 1 vector with a 1 in position I, then Z tilde of EI is just going to be my ith row vector of Z. So let me actually write out the rows of Z. I'll call my rows Z1 through Zn. So now if I apply Z tilde to this 0, 1 vector, EI, then Z tilde of EI just gives me Z sub I. And okay, and now if I draw, so remember, I've required my matrix Z to have maximal minors positive. And so what that will mean is if I draw my vectors Z1 through Zn in P2, then they must be in convex position. That's what the positivity of the minors tells me. So let me just write that. So positivity of the minors of Z implies the Zi's are in convex position. And we have that EI always maps to ZI. But now what I'm really interested in is the image of my vector A1 through AN under this map. And A1 through AN is just a positive combination of the EIs. And so a general point A1 through AN is going to get mapped to a positive combination of these ZIs. So as the AIs vary over non-negative reals, the image gives all points of this polygon viewed in projective space. Okay, so this is the example when k is 1 and m is 2. And more generally, if k is 1 and m is arbitrary, then the amplituhedron, which lies in GR1 m+1, i.e. projective space of dimension m, is combinatorially equivalent to a cyclic polytope with n vertices in Pm. Okay, now. Any questions so far? Oh, and I'll add one more example to this list. So if we take instead the case where m equals 1, then the amplituhedron is homeomorphic to the bounded complex of a cyclic hyperplane arrangement. In PK, and this was a case that was worked out in joint work with Stephen Karp. Okay, now from the point of view of physics, m equals 2 and m equals 4 are the most interesting. So that's what I'll be talking about in my next couple of lectures. It's been a while since I've used these squeegee things, so if you have any pointers on technique, you're also welcome to let me know. Okay, now let me just say a little bit about our notion of triangulation for the amplituhedron, because that's going to take us back to the physics applications. Okay, now the amplituhedron, despite the name, it's not a polytope. Yeah, so we can't really talk about triangulations, but we can talk about something that is a bit analogous. So recall that we have this expression. We have this decomposition of the TNN Grassmannian into cells. And we also have this surjective map from the TNN Grassmannian onto the amplituhedron. And the TNN Grassmannian has dimension k times n minus k. And the amplituhedron, which sits inside the Grassmannian of k-planes and k plus m space, has full dimension here. So this has dimension k times m. And in general, by our choice of n and k plus m, right, we required that k plus m is at most n. In general, this number is going to be bigger than this number. But what we would like to do is understand this object, the amplituhedron, using cells of the correct dimension on this side. So this has dimension k times m. So what we want to do is find a collection of k times m dimensional cells here, such that z tilde is injective on those cells, and such that the images of those cells fit together nicely to tile the amplituhedron. So let me make some definitions. So if Z tilde is injective on a Km dimensional cell, Sm, then we'll say that Zm, which I'm defining to be the closure of the image of that cell, is a tile for the amplituhedron. So yeah, so we are interested in particular in the Km dimensional cells over here, such that Z tilde is injective on them. And when we find such a cell, then we look at its image and we take the closure and we call that a tile. And now a tiling of the amplituhedron is a collection, Zm, of tiles such that their union is the whole amplituhedron and their interiors are pairwise disjoint. So this is going to be our notion of triangulation. But there's nothing, there's nothing polytopal here, and there's nothing to do with simplices here. But this is how we would like to understand the amplituhedron.
Sorry.
Uh-huh.
Do you have some notion of how the tiles should intersect? Not the open part.
Yeah. So sometimes we ask for something stronger. So we define a good tiling to be a tiling where if two tiles do intersect, you want them to intersect at something that's like a common face of both. So in general, we won't require that for a tiling, but in some of the things we do, we talk about good tilings, and then we care about how things intersect. Yeah. Okay. Sorry? Good question. The question was, do tilings always exist? And they don't. They don't. So for m equals 1, for m equals 2, and for m equals 4, there are many such examples. And for a particular value, for a fairly small n and k, and for m equals 6, we already have an example where a tiling doesn't literally exist. Yeah. There's some kind of weakening of the notion where you can, there's something weaker that happens, but in general, tiling as I've defined it doesn't exist. But for m equals 1, 2, and 4, it does.
And one of the two properties does not work?
Say it again?
Which one of the two properties does?
I forget the details, but I could try to say more after if you like. Okay. All right, so now just to go back to the motivation of the amplituhedron, the statement, the claim that the volume of the amplituhedron computes scattering amplitudes is very closely related to the statement that certain collections of BCFW cells in the TNN Grassmannian give a tiling of the m equals 4 amplituhedron. Okay, so somehow it was basically more or less this statement appeared in the first paper of Arcani, Hamid, and Trinka. Basically their sort of reason for the definition of the amplituhedron, or the reason the amplituhedron was the right thing, boils down to the conjectural statement that certain distinguished collections of cells in the TNN Grassmannian give a tiling of the amplituhedron. And actually, in that first paper, they conjecture that there are many different tilings of the amplituhedron. And one such tiling was proved for the first time in a paper of Evan Zohar, Leclerc, and Tesler. So one such BCFW tiling was given in their paper from 2021. And then in recent work with them, together with Matteo Parisi and Melissa Sherman-Bennett, we showed that all conjectural BCFW collections of cells in the TNN Grassmannian actually do give tilings of the amplituhedron. So I'll say more about this in my third lecture, but not any more about it today. Oh, wait, that's not what I meant to do. Okay. All right, so now what I want to do is shift gears and give a quick introduction to cluster algebras. Oh, question? Yes, yes. So let's see. We don't. Yeah, the things that we get here don't need to be regular. Yeah. The notion of tiling is fairly relaxed. It's fairly weak. Yes. Okay, so next I want to define cluster algebra, because cluster algebras and cluster coordinates wind up being very closely connected to the study of the amplituhedron. And in particular, the m=2 amplituhedron is very closely connected to the cluster structure on the Grassmannian of two planes in n space. And the amplituhedron for m=4, its structure is very closely connected to the cluster structure of the Grassmannian of four planes in n space. So basically, the idea is that the little m parameter in the definition of the Grassmannian, in the definition of the amplituhedron, that m, maybe let me just write something. So this amplituhedron is closely connected to the cluster structure on the Grassmannian of m planes in n space. Okay, so that's a theme that we'll see in the next two lectures, but first I should just define cluster algebra. So apologies to those of you who have seen this definition many times before. Okay, so cluster algebras were defined by Fomian and Zelevinsky around the year 2000. A cluster algebra is a particular kind of a commutative ring with some distinguished generators. And these cluster algebras have a very rich combinatorial structure. There's also a geometric analog notion of cluster variety, which is roughly a variety whose coordinate ring, homogeneous coordinate ring, has a cluster algebra structure. Okay. So cluster algebras are defined using quivers. So a quiver is a finite directed graph. Multiple edges are allowed. Oriented cycles of length 1 and 2 are forbidden. And there are two types of vertices. There are the mutable vertices, and there are the frozen vertices. So let me draw a picture here. So I will denote mutable vertices by dots, and I will denote frozen variables by little squares to remind you of frozen ice cubes. So here are some arrows. Multiple edges are fine. Okay. And, okay. And, all right. N will be my number of mutable okay. Fomin and Zelevinsky use N and M for the number of mutable vertices and the total number of vertices. This should not be confused with the N and the M of the amplituhedron. I could try switching notation right now, but I'm not sure if I could succeed in carrying it through without a mistake. Okay, so, all right. Now I want to define quiver mutation. Okay, so quiver mutation is an operation that I can perform if I choose a quiver and I choose a particular mutable vertex. So okay, so here's quiver mutation. Let's let K be a mutable vertex of Q. Then we can mutate at K to get a new quiver that we'll denote by mu sub K of Q. And we perform quiver mutation. Quiver mutation is obtained by 3 steps. First, for each path of length 2, whose central node is K, we introduce the edge J to L. Then we reverse the direction of all edges incident to K. And finally, we remove oriented 2 cycles. Okay, so let's take Q to be this quiver, and let me draw another copy of it down below, and then we'll start doing this. We'll start mutating at it. So let's say that this is my vertex k. Then the first thing I'm supposed to do is look for all paths of length 2 whose middle node is k. So I have 2 paths of length 2 that do this, and for each one I need to add a new arrow from the start to the finish. So I should add 2 arrows like this, and then I also have a path of length 2 that does this, and so I should add a new arrow going from the start to the finish. Okay, so I just performed step 1. Now I reverse the direction of all edges incident to k. So this one will go the other way. These will go the other way. This goes the other way. And now finally I remove oriented 2 cycles, and I have an oriented 2 cycle here. So I can cancel this white arrow with one of the orange ones. And this is what I have left. So this is mu sub k of q. And it's important to note that mutation is an involution. So if I mutate twice at the same node, I get back to the original quiver. Okay. And then we say that 2 quivers are mutation equivalent if you can go from one to the other by a sequence of mutations. Okay, now there's also an algebraic counterpart for quivers and quiver mutation, and that's going to be the notion of seeds and seed mutation. So we let F be a field of rational functions in M independent variables over C. And then a seed in F is a pair consisting of a quiver together with what's called a cluster X, where Q is a quiver with n mutable vertices and m minus n frozen vertices. And this X bar is an extended cluster, which means an M tuple of algebraically independent elements of F indexed by the vertices of Q. So a very boring example would be perhaps our quiver is this type A3 Dinkin quiver, and our extended cluster could just be the labeling of vertices by x1, x2, and x3, and we'd consider this a seed in the field of rational functions in algebraically independent variables x1, x2, and x3. Okay, so a seed is basically a labeling of the nodes of a quiver by algebraically independent variables, by algebraically independent rational functions. Okay, and just as we had this operation of quiver mutation, there's also an operation of seed mutation. So let's let k be a mutable vertex in Q, and let's let xk be the corresponding cluster variable. Maybe I should say, yeah, the elements in x bar are called cluster variables. So in this example, each of x1, x2, and x3 are called cluster variables. So then, the seed mutation, uk, from qx to q prime, x bar prime, is defined as follows. So our new quiver is what you get when you mutate the old quiver at vertex k. And then this new extended cluster is nearly the same as the old cluster, but we're going to throw in one new cluster variable indexed by the vertex k, and we're going to remove the old cluster variable associated with node k, where xk prime is defined by the following equation. So xk times xk prime, so the old times the new cluster variable, labeling the kth node, is equal to the sum of two monomials, and one monomial is associated to the set of all arrows in the quiver pointing to k. The other monomial is associated to all arrows in the quiver pointing out from k. And we're just multiplying together the cluster variables on the other side of that edge. Okay, so seed mutation is a new seed where the new quiver is obtained by mutating the old quiver at node k. And our new extended cluster is obtained from the old extended cluster by swapping out xk for xk prime, according to this relation. Okay, and just as before, seed mutation is an involution. Okay, so so remark, seed mutation is an involution. Okay, so now I can finally define cluster algebra. So we can let sigma be a seed with my extended cluster equal to some set of mutable variables called initial cluster variables together with the frozen cluster variables. And then we let chi be the set of all cluster variables obtained from X by all possible sequences of mutations. And we'll let R be our ground ring consisting of Laurent polynomials in the cluster, in the frozen variables. And then finally, the cluster algebra associated to our seed is the ring generated by all cluster variables with coefficients in the ground ring. So this is going to be a subring of the field of all rational functions, F. So this is the R subalgebra generated by all of our possibly infinite cluster variables. Okay. And let's see. I guess I have 3 minutes left. Okay. So I'll just mention then, let me just give myself a little more space right here. So everyone's favorite example is that of the Grassmannian of two planes in n space. And a way that we can get a seed for this, so we can talk about the Grassmannian of two planes in n space, and then we can talk about the coordinate ring of the affine cone over the Grassmannian. So this is the homogeneous coordinate ring, and this is generated by the Plucher coordinates P sub ij, where I is less than j. And so we can get an initial seed for this cluster algebra by taking a triangulation of the n-gon and then what I do to get a quiver is I put a mutable node on every diagonal. I put a frozen node on every boundary segment, and then I inscribe directed triangles, say oriented clockwise, in all of my white triangles of my triangulation. And then my cluster variables and frozen variables get labeled by Plucher coordinates. So since each vertex lies on a diagonal or a side, I can label it by the corresponding Plucher coordinate. And this one is P2, 4. And then the claim is that this gives a seed for a cluster algebra, which can be identified with the homogeneous coordinate ring of the Grassmannian. And it's a nice exercise to check that mutation of a triangulation, so mutation at a node in my orange quiver corresponds to flipping a diagonal in the triangulation, and the exchange relations, this algebraic relation here, exactly corresponds to a 3-term Plucher relation. And then we will see, so I guess I didn't write down the definition, but if I have a collection of cluster variables that appear in a given cluster, they are called compatible. And compatible collections of cluster variables exactly correspond to collections of non-crossing diagonals in my polygon. Okay, so I think I should stop there.